Hi, and welcome to Module 3 of Lecture 4. In this module, we're going to cover the Logit model, which we use for the fourth category of hypothesis test that we left blank earlier. We use it when we have a binary dependent variable, like vote or not, and a continuous independent variable, such as age. If you think back to the 2x2 table of types of hypothesis tests we discussed in Lecture 2, we had a dependent variable and an independent variable type. Here we have a categorical dependent variable because it only takes two categories here, but a continuous independent variable type. In this table, we wrote down probit or logit, but never mentioned what they are. Here we'll talk about what they are. And what they are probability models. The types of probability model. Not the only types, but two commonly used types of probability model. A probability model is a model in which we only observe a 0 or 1 for the actual values of the dependent variable, but we believe there's a latent or underlying propensity to take that action, the action of a 1, to have a 1 on the y, and all of our analysis is going to be looking at what increases or decreases that latent propensity to take that action. Something that increases or decreases your underlying chance of getting a 1 for y. We're going to talk about logit only, but probit is very similar except for its functional form. Okay, some assumptions on the O.L.S model. First, though, to get a sense of why we have to introduce the logit. One assumption was linearity. We assumed that a straight line adequately represented the relationship in the population. If we try to fit a linear model to a nonlinear relationship, we're going to get biased estimates, and we saw that when we had sleep and grades. We saw that if we tried to just fit a line and then take into account that it was decreasing at the end, we got biased estimates. The second assumption is normality. We assumed that the errors are normally distributed or t-distributed, and that implies that the dependent variable is also that distribution. That assumption on the distribution limits the kind of dependent variables we can use. Our dependent variable must be interval ratio level, it must be continuous, and it must be unbounded. There are very few variables to meet these criteria, right? Very few variables have no limits in either how big or small they get and are completely continuous. A lot of the examples we used before, like the 1 through 5 scale we used in the previous module when discussing feelings towards the environment, are not continuous and are not unbounded. And they're actually categories, not even interval ratio numbers. That said, often we get close enough. It turns out O.L.S is very robust as a rule, and if we have enough categories and if we believe strongly the meaning separating each category value, so between 1 and 2 and 5 and 6 and so on, if that meaning of that difference is kind of the same between different categories, we can often get away with O.L.S anyway. That said, it's more difficult potentially with dichotomous options that are more extreme. We have only two possible values, so it's definitely not continuous, it's definitely bounded, and it's barely a number. It's a 0 or 1, which is kind of an arbitrary way of labeling two different values, a yes or no. And there are a lot of examples like this in social sciences, right? Like, did someone vote or not? Did a pair of countries, which is called a dyad here, go to war? Did a country sign a treaty or not? You should be careful in these cases and using O.L.S with a dichotomous dependent variable because you're going to violate assumptions of O.L.S. However, if you go forward and do this anyway, which many people do, you'll be using a linear probability model, which is actually quite common in economics, in part because of interpretability reasons, as we'll discuss in a second. We did this before ourselves without ever mentioning it in our vote choice examples. We had 0 or 1 chance of voting for a particular candidate, and we just interpreted the effect of some x on the chance on individual candidates and voting for the individual candidate by saying, oh, well, because this beta was positive, doing this thing over here increases my chance of voting for the candidate. When in reality, all we had for data for a dependent variable was a 0 or a 1 for whether or not you voted for the candidate or not. So we automatically interpreted it in this probability way without ever discussing why. So we'll do that now. If we just take a dichotomous dependent variable and apply our earlier example of a regression, so y equals alpha plus beta x, and code the 0 or 1 as the dependent variable for a single independent variable that's continuous, right? The way we interpreted this before, and the interpretation we use in a linear probability model, is that a 1 unit change in x results in a beta unit change in the probability that y equals 1. To see why that is, we're going to go through a pedagogical example. Here's the hypothesis. The more Democrats who live in a congressional district, the more likely it is that the Democratic candidate will win. The data here come from the 2008 congressional election data. The dependent variable is dichotomous. 1 is the Democrat one, 0 is the Republican one. The independent variable is continuous. It's the percentage of the district that identifies as Democratic. Here are some O.L.S results. We get an estimate of 0.021 with a very small standard error, it's a decent sized sample, and a large t-value, so we can reject the null hypothesis in this case that the percent Democratic in the district does not affect the chance of voting for the candidate, which kind of makes sense. Partisanship is important for vote choice. How do we interpret that? Well, each percentage point increase in the probability in the percentage of the district that is Democratic, that's this thing, results in a 2.1% increase in the probability that the Democrat wins. Note here that 0.021 means a 2.1% increase in the probability that the Democrat wins. That's our interpretation, right? It's not necessarily obvious from looking at the model, right? The model says y is 0 or 1. If I'm trying to predict what's happening, right, and I predict that I get a 2.1% increase in y, what does that mean exactly, right? Y can only be 0 or 1, right? What does a 2.1 increase in getting a 1 mean in that context? If I were to draw it, it makes it even a little more confusing, right? Here are our data. Our data are either Democrat 1 on the top or Republican 1. They're all 0s or 1s. Our predicted model says there's a 2.1 percentage chance increase in the probability, right? Or 0.02, right? In terms of actual probabilities, right? Not percentages. So that looks like this. That looks like this dark line here in the middle is that fitted line. That's this line right here with 0.021 for beta. We see it's nowhere near any of the data, right? There's a little over here and there's a little down here, but in general, it's way far from all the data. So what am I exactly saying when I say that if I increase the percentage of a district that is Democratic by 1%, I get a 0.021 increase in the probability Democrat wins, a 2.1% increase in the probability Democrat wins? What I'm saying is I believe there's some underlying latent propensity to vote for a Democrat, and as the district percentage increases, that propensity increases. So since this is random in effect, since this is a random variable, since the vote is a random variable, that chance that a y is drawn in that by that random variable is increasing the more of a district is Democratic. So I'm proposing an underlying process by which the chance you draw a y, the chance a y equals 1 rather, the chance a Democrat wins in that district is dependent on the proportion of the district that's Democratic. And as I increase that proportion that's Democratic, I increase the underlying chance that that district votes Democratic. That's what I'm proposing here. That's the interpretation in a linear probability model. There are a couple problems with this, though. And if that wasn't clear, you might want to go back and think about it some more and go back and listen to it because it's a complicated idea. But there are a couple problems with this. The second one we saw already. The data are nowhere near the line. The first one is you get impossible probabilities. So if I increase the proportion of the district that's Democratic past about 75 or so, and there's a lot of data like that, my chance of winning exceeds 1. That's not possible, right? Despite the common use of 110%, that doesn't exist, right? Like you can only happen with certainty. There's nothing more than certainty here, right? Similarly, if I go down below about 24 or 5 or so, the chance of winning goes below 0, which also can't happen. So these are problems. And this is problems because we failed to account for the assumptions inherent in O.L.S. Now, you might say, I don't care that much about these problems because this linear probability model was really convenient to interpret, right? As long as I believe there's an underlying latent propensity to do something, I can talk about how increasing my independent variable increases or decreases that underlying propensity. That's straightforward. I don't have to bring up any complicated math, as we'll see in a second. That's your choice. People, as I said before, plenty of people use linear probability models for one reason, because of that ease of interpretation. But we can also transform the typical O.L.S model to estimate models that take into account different distributions of the dependent variable. And we can have many kinds of models with different distributions of the dependent variable, and we'll still be able to understand what the relationship is between the independent and dependent variables using the stuff you learned already in this course. And that's key, and that's what we'll talk about in the next module, really. We can see it here as well. And logistic regression, or just Logit, is one of those transformed models. I should say logistic regression is super common in machine learning approaches and data science. So this comes up a ton if you go on to that direction of job, I guess. Logit and Probit are proper models for dichotomous dependent variables. So dependent variables that take only two different values. Here's the equation for Logit. Y equals 1 over 1 plus the exponential raised to e here is 2.71828 something or other, raised to the negative, and here's your original model. So it's raised to the negative alpha plus beta 1 x1 plus beta 2 x2 and so on. This is what the Logit model is. So you take your original prediction for y hat and you stick it, you raise your exponent in the denominator here to the negative of that original prediction. This is going to lead to complications in interpretation, as we'll discuss in a second, but we can still use this Logit and talk about how this works. We're going to do a z-test instead of a t-test to test for significance as before. As we talked about before, the same z and t are the same with large sample sizes. So these tests are the same with large sample sizes. We in general should avoid using Logit here with small sample sizes. The critical values are the same as before. For a two-tailed test, it's 1.96. For a one-tailed test, if you knew which direction you expected the coefficient to be in, positive or negative, it'd be 1.645. We can run the same approach with the Logit instead of the linear probability model. All standard like R and Stata and other standard statistical packages have Logit built in. You just run a Logit instead of a linear probability model. You get a different estimate for the Democratic candidate. You get a standard error. You get a z-value. The z-value tells you, as before, if this independent variable is a significant predictor of the dependent variable. It is, in this case, so as before, we can say again that it can reject the null hypothesis that the percent Democratic in a district leads to a change in the probability that the district votes for the Democrat. I don't know if I said that correctly, so I said it again. We can reject the null hypothesis that the percent Democratic has no effect, on the chance that the district votes Democratic. So that's all the same as before. So even though we've never used Logit before, and I haven't really shown you how to do much with it now, I gave you an equation like 3 seconds ago, we can still interpret how this works and what this means in terms of significance using the stuff we knew before. Nothing has changed in that context. What has changed is how we interpret the coefficient, the estimate of the coefficient. It is no longer the case that a 1 unit increase in x produces a beta change in the expected value of y, or even in the expected probability of getting a value of 1 for y. So whereas the linear probability model kept a nice interpretation in which a 1 unit increase in x led to a beta increase in the probability of getting y equals 1, a 1 unit change in x does not produce that beta change in y. It is more complex than that. And in general, to make your life easy, you want to use established techniques that are usually hard-coded into these software packages or packages that you can download for your software programs for stats in order to calculate the margin rate of change of your of the percent of voting for the Democrat in that district as a function of the percentage Democratic in that district. The reason is, and before I go to this one, the reason is what we're doing is to calculate the change of y with respect to x1, it's a derivative, remember. So we take the partial derivative of y with respect to x1. That is no longer just beta 1, because now we have a complicated function of x1 that's not just x1 times beta, it's 1 over 1 plus eta of this thing. So we must take the derivative of this thing to get out the marginal effect of x1 on beta, on y rather, and on the probability of getting y equals 1. We'll talk about that a little at the end in the problem session, but not much. Okay. The predicted line from the logit looks like this. The logit and the probit are both S-shaped curves, which means they look kind of like an S. And we see that the minimum is 0 and the maximum is 1. So they can't go below 0, so you never get impossible probabilities in that direction, and they can't go above 1, so you never get impossible probabilities in that direction. To see what it is, we go back to this equation. As these things get huge, this goes to infinity. E to the negative infinity is 0, so y is 1. As these things go to a negative infinity, you get e to the infinity, which is infinite. You get 1 over infinity, which is 0. So the logit is bounded between 0 and 1. So it can actually represent a real probability. We also see that we get closer to a lot of these data. Not all of them, but a lot of the data, we're closer to the actual data in the that we actually obtained. And in comparing the two different lines, we see that the vertical line here is further from the data and yields impossible probabilities. The logit does not. So one more example to conclude this module. The dependent variable here is, did a particular respondent in the National Election Survey study vote? It's dichotomous, 0 or 1, not vote or vote. The two independent variables here are education, which is a five category variable, and gender, which is a dummy variable, taking the values of 0 or 1 for female or male. I think we actually switched it in the next one, so sorry. I think 1 was female here. And usually in the past, they only used dichotomous dummy variables for gender. I believe that's changing now. Actually, sorry, this is male for one in this example. What do we get? Well, we get estimates in the O.L.S version of this. The linear probability model gives us these estimates. The logit model gives us these estimates. They're similar in terms of significance. So education here seems significant, strongly. Gender does not. Here, again, education significant, gender not. So that's all the same, and we got the same outcome. Interpretation, though, is going to be different. We talked about interpretation before, abstractly. Let's look at differences in prediction now. On the left are predictions arising from the ordinary least squares model. And these are predictions in terms of what proportion one has of voting under different characteristics of the individual. So for no high school, here's a comparison across gender. For high school, comparison across genders, and so on and so forth. A few things to note. One, you get over 100% over here. And it was men who was the one, I guess, in this case. Sorry about that. Second, the difference in gender is constant across educational categories. And the difference in educational categories is constant across gender. So every step between any different value of the independent variables is constant, as it must be for a linear regression. Right? As you increase the independent variable by any particular unit, you increase the dependent variable by that beta, by a constant amount. The logit, however, does not have that same property. One, these are all real probabilities, they're not 100.7. But two, there's a different increase based on where you are. So the effect of education here depends on whether the person is male or female. So you get an automatic interaction between the two different variables. So the effect of one variable must, in a logit, affect the effect of the other variable. You automatically have interactions happening in logit models. And that's also because of the form of the logit, as we'll also talk about briefly in the problem session. Okay, that was a long one. That covers the logit model. Again, this is only introduction to this. If you go on in social science or in, say, data science, you spend a lot more time with the logit in all likelihood. But for now, we're going to go on to a very short ending module here, talking about other kinds of regression models that exist in the world. And then we'll conclude this lecture and the whole course with a short problem session going to some of the math behind some of this stuff we talked about so far. Thank you very much.